Hey guys, I forgot to record. This is how you do the first one. It's just easy, just plug and chug. We're working on this one. We're getting a different answer than on the slide, so I'm double checking to see if we use different values. So, let me see here. So in your Google Classroom, under our thermodynamic quantities, let's see, I bet that's the problem. I bet they are different on this resource. Joe, not okay. It's like we're in kindergarten. They do need separating. You just attacked me. All right, so looking at this one, let's see, NO2 gas 51.3 versus N2O4 99.8. So I bet I used this resource, not the other resource, because when I did it, those are the values I used. So we'll just go with the ones that are on our sheet. So what'd you get? 5.4. And remember, that's in kilojoules, because our moles canceled. So now we're going to use that K equation, which we just saw on the previous page. K equals inverse natural log to the negative delta G divided by RT. But we have to remember that our R, when we look at our equation sheet, our gas constant is in joules per mole. So we need to convert our delta G from kilojoules into moles. So that's going to be 5,400 joules. That's not really working. Let's put the light up there. See if that works. So plug in e to the negative 5,400 joules divided by 8.314 joules per mole Kelvin times our temperature, 298 Kelvin. Technically, we should have our units canceled and end up with no units, so our Kelvin cancels. Let's see, if we've made this joules per mole, it would cancel. Yeah. So, oh, yep, sorry. Yeah, it's really sloppy too. So 5,400 divided by our gas constant, 8.314, times our temperature in Kelvin, which is 298. You don't have to use the units here because, remember, K doesn't have a unit, but just to show that it would cancel out, I included them. I also put the R and T in parentheses because if you don't do that R times T first, you will get the incorrect answer. So I put it in brackets in my calculator. So inverse natural log, negative 5,400 divided by parentheses 8.314 times 298. Syntax, what's it saying? Oh, I need another parenthesis. What? E. What am I doing wrong here? You got 0.1. Point what? 0.113. 0.113. Oh, so again, we're going to have a different answer because of my differences here. Let me see. Why am I getting the wrong answer? I was talking about Oh, I got 0.1132. Is that what you guys said? That's what Owen said. Ashlyn, what did you say you got? The wrong answer? What did you get? I typed it in wrong. Oh, okay. Okay. So we got K equals 0.113. And again, no units. So just leave it like that. This next one is similar to the one we just did. The one on the right is similar to the first one we did. Do you want to do another one, or do we feel okay on those? Feel okay? All right. If we flip to the next page, when we think about thermodynamics, really we're just thinking about the change in energy of the reactants and products, and if a reaction is favorable based on that energy change. But it can't tell us anything about speed. It doesn't tell us about activation energy. It doesn't tell us if there's multiple pathways. So it can't tell us about the speed. We have to consider kinetics. If the reaction is thermodynamically favorable, but does not occur at an appreciable rate, then it's considered under kinetic control. So if you look here, thermodynamics determines the initial and final state in terms of energy, and it helps us determine spontaneity. Kinetics tells us those intermediate states, the activation energy, and thus the speed. So when we look at Gibbs free energy, this change from reactants to products, it's going to be negative. So it's going to be thermodynamically favorable, but it can occur really quickly or really slowly based on this kinetic control. Let's see. If a reaction is under kinetic control, it has a high activation energy, which could be due to unfavorable orientations or a high number of molecules not colliding. So if we look at this question, we're given a reaction, we're given an enthalpy change, and we're given a Gibbs free energy. It says, consider the reaction represented above when equal volumes of N2 and H2, each at 1 atm, are mixed in a closed container. No formation of NH3 is observed. Which of the following explains that? Option A says N2 and H2 must be mixed in a 1:3 ratio for the reaction to occur. We know that is not true, right? You can have any amount as long as you have some of each, the reaction is going to occur. Doesn't have to be 1 mole fourth, like the reaction is going to occur so that 1 mole of reactant is going to react with 3 moles of reactant, but you can have 1 mole of each. It'll just proceed until your limiting reaction is all used up. So that one's not true. A high activation energy makes the forward reaction extremely slow. That is a possibility because we know in terms of enthalpy, it's favored. In terms of Gibbs free energy, it's favored. So this is a possibility. So I'm going to put a little star by that. The reaction has an extremely small equilibrium constant, thus almost no product will form. It could be small, right, and almost no product would form. So that is kind of a possibility, but that doesn't, that's not the best option, right? The reverse reaction has a lower activation energy than the forward reaction, so the forward reaction does not occur. That can't be possible since our enthalpy is negative. So we've narrowed it down to B and C. Let's see. If it had an extremely small equilibrium constant, almost no product would form. That is still not going to affect the speed. You would still see product form. So the one that makes the most sense is that B, where the reaction, even though it's favorable, it has to overcome that activation energy barrier. And so it would take a long, long time. This one isn't necessarily kinetics related. Activation energy is kinetics. All right. So something that we can do to provide a more favorable procedure is we can use coupled reactions. So coupled reactions are an external source of energy, such as electricity or a battery, that can be used to overcome Gibbs free energy and drive the reaction forward. An example is the decomposition of water. So if we just set water right out, it's technically at equilibrium. It's going to autoionize, but it's not going to decompose into hydrogen and oxygen. We have to use electricity to force that reaction to occur. Remember when we did gel electrophoresis and we saw those little bubbles on the sides? We applied a current through the buffer. That was what we were doing. Another one, the formation of glucose from carbon dioxide and water is not spontaneous. It takes in that energy from the sun, that sunlight. If you remember drawing out cellular respiration and photosynthesis, right? So we needed light for that one. Another way to force a non-spontaneous reaction, we just talked about that, is your coupled reaction. Here's some more examples. Biological systems. So we, like plants, animals, we use the formation of ADP, and that is not favored. It's coupled with that cellular respiration that creates the ADP, and releases energy that is then used for the formation of ATP. Let's see. That's kind of it for for lecture 43. Lecture 44 starts with oxidation number before it gets into electrochem and essentially batteries, galvanic and voltaic, and there's another type. Do we mention it in here? Galvanic, voltaic. Did I mention the other one? Let's see here. Galvanic, voltaic. Galvanic, voltaic. Electrolytic. Yeah, at the very end, we'll talk about electrolytic. So let's pause here for today, and then Monday we'll pick up with the cells, and then the very last lecture, 45, is super short, so we'll try to get that as well. We'll see how it goes. But again, we're going to skip the Unit 9 exam. It'll be on the final. People asked for the final to be Unit 9 heavy. When I actually looked back over the final, I think it's easier than Unit 9. It's heavy on stuff that you theoretically should know. Like, it's the key stuff from chemistry. So like naming, stoichiometry, like what I would consider the easy stuff. So if we want it to be Unit 9 heavy, I can make it Unit 9 heavy. But maybe what I'll do is I'll pass out the original review and we'll see how we feel about it. And then that way, if we don't like it, I can add in more Unit 9 stuff. But I would say adding Unit 9 stuff is going to make it harder. So we can talk more about that. I am also going to pass out some stuff to get you started for the AP exam review. So the first thing is just going through the different units. So kind of looking back and seeing what topics, what sections were in each unit. This does go by the AP exam order. So remember, we combined Unit 4 with Unit 1. So So you're going to see a little difference there, like we didn't have a unit 4. Other than that, everything pretty much matches. They don't necessarily go in order of lecture, though, because some things fit together differently. Then the next one is kind of the write this, not that. So as you're thinking about free response questions, these are the things you should not write. Here's how you should approach those questions. So there's a bunch of them. There's just kind of general ones and then broken down by unit. And then finally, this last one is kind of key points from each unit. So what are the things that you need to remember from each unit? So kind of the, not questions, but general, like, hey, think about this. Make sure you know this, okay? So I'll pass that out so you can start looking through it. We'll do official review next week after we finish Unit 9. And yeah, that's the plan. Questions? Yeah.
I know that.
Yeah. So the rest of the time is filling in the rest of the notes and working on your POGIL, which is due Monday.